Okay, here we go. Let's continue talking about three-dimensional vectors. So here we go. Changing to writing mode. Changing my window capture. Oh, there we go, 101C. Awesome. Okay, so where did we leave off when we finished last week? Oh, so we were still talking about the cross product. Okay, so I've given you this formula for the cross product. And it looked like this. Like if you have a vector u, if you have a vector u with components u1, u2, and u3, and you have some other vector v with v1, v2, and v3, we found that the way you find u cross v is really interesting. You get a new vector where, so you have this formula where it's like if you're working on the first component, it will involve the second and the third component. You'll do, and then you take one of them at a time and subtract the other one. So u2 v3 minus u3 v2. So notice I'm doing the first component. It uses the second and third components to do it, and then they come in pairs. So you have like 2 and 3, 2 and 3. You subtract them. So for the second component, I'm going to use the first and third. So I'll do u1 v3. Oh yeah, u1 v3 minus u3 v1. Put a minus in front of it. And then for the third component, I'll use this first and second. So you would do u1 v2 minus u2 v1. Okay, and I sort of showed you where this came from a little bit, and we're going to talk about, well, where does this formula come from? And it has something to do with something called a determinant. So we're going to talk about what are determinants. Okay. So determinants are something that you do to a matrix. So determinants are a scalar computed from a matrix, which leaves you to wonder, well, what is a matrix? Well, for our purposes, a matrix is a collection of vectors of the same size. So let's talk about that. Okay, so, oops, I hear someone's stuff in the background. I'm going to silence them. There we go. So let's start off with the smallest vector you can have, a size 2 vector, a 2-component vector. So u1, u2, and v1, v2. Okay, so there's two ways you can do this. You can make a matrix by putting the vectors as columns of the matrix. So I would write the first component, the second component in a column. You see how the numbers are stacked on top of each other? And then I could take the other vector, first component, second component. So a matrix is just a collection of numbers, and usually when you're dealing with a matrix, you put square brackets around it. So I could call this the matrix A. So how is this matrix made? By taking, oops, I just want to type right here. It's not letting me. There we go. So this is called a column vector matrix. Because what I did is I took my two vectors and I entered them. No, this is 2, 3. Or 2, 4, my bad. We're still continuing with the cross product. So how did we make our matrix? We entered the vectors as columns. Now you could go another way. You could make your matrix by saying, oh, let's do U1 and then to the right U2. And then you could put your other one V1, V2. We could call this matrix B. So how did we form this vector? Well, we formed it by inserting the vectors along a row. You could do it either way, but it's most common to enter your vectors as columns. Either way works though. So like as an example with numbers, I don't know, let's say that you have the vector U is going to have components 1, 2. And V is going to have the components 3, 4. So you can make a column vector by taking U and entering it as a column, and then taking V and entering it as a column. So my first column will have 1, 2. My second column would have 3, 4. Okay. Now, this is called a 2 by 2 matrix because it has 2 rows and 2 columns. Okay, and now because we're entering the vectors as columns, this is going to be the number of vectors. Right, I have a column for each of my vectors. I worked with 2 vectors. And then the rows are going to be the number of components in each vector. .103 is like a whole class about all of this. We're only going to get into the very basics of this. Okay, it's sort of important when for us, you could have matrices of like different sizes. Like you could, so like this is a 2 by 2 matrix. We have 2 rows, 2 columns. You can have like all sorts of different numbers, like 3 rows and 4 columns, or 1 row and 5 columns. For us, though, in this class, we're only interested in what are called square matrices, which are n by n, i.e. the number of rows and columns is the same. So like a 2 by 2 is a square matrix, a 3 by 3 would be a square matrix. So how would you make a 3 by 3? Well, you'd have to have something like this. You would have a U vector with components U1, U2, U3, a V vector with components V1, V2, V3, and then a W vector component W1, W2, W3, and then you would make your matrix by plopping U in a column, your U1, U2, U3, and then you would plop V in a column, V1, V2, V3, and then you would plop W in a column, W1, W2, W3. We call that the matrix C. So this is a 3 by 3 matrix. Why? Because you've got your 3 rows and your 3 columns. In other words, there's 3 vectors that started with 3 components. Okay. So, let's talk about how do you compute these determinants. So, whenever you draw a matrix, you usually put square brackets, but if you want to calculate the determinant, you put they look like absolute value brackets, they're just vertical brackets, or just a vertical line. So let's make a row, let's do this as a row matrix. We'll do U1, U2, U3, entered along a row as opposed to a column. V1, V2, V3, W1, W2, W3. Okay, so I made a matrix by entering my 3 vectors along the rows. And I know that I want to take the determinant because it has the vertical lines around it as opposed to the brackets. Okay, now the determinant is really interesting because it's a recursive operation. And I'll explain what I mean. So what the determinant is calculated recursively. So what that means is, for example, if you want the determinant of a 4x4 matrix, then you will create smaller 3x3 matrices and calculate their determinants. Okay, and then to calculate the determinants of the 3x3 matrices, you will create smaller 2x2 matrices and calculate their determinants. So the way this works is that you start off with some size of matrix, like a 4x4. That 4x4 will be broken into smaller 3x3s. You'll calculate their determinants. Well, how do you calculate their determinants? You break those into smaller 2x2s. Okay, so you start with something really big and you break it into smaller and smaller pieces. That's what we mean by a recursive definition. Okay, so the basis of all of this is how you calculate a 2x2 matrix determinant. So if you have a 2x2 matrix with entries A1, A2, B1, B2, we talked about this before, you multiply along the diagonals, so you're going to get A1, B2 minus A2, B1. And where have we seen this before? Like what we see here. This formula. Where have we seen it before? Yeah. You remember how it alternates? How we have like A1, B2, A2, B1? Okay. So calculating the determinant of a 2x2 matrix is done this way. So let's do an example with a 3x3 and we'll show you the recursive definition. So let's say you're calculating the determinant of a 3x3 matrix, which is going to be 2, 5, -1. Then we'll have another row, -1, 1, and 3. And we'll have another row, -2, 3, and 4. So we want the determinant of this. Okay, so the way this works is you start with this number right here, 2. So this is called expansion by minors. So this 2 is in row 1, column 1, right? It's in the first row, and it's in the first column. So do you see how if I cross out the first row and the first column, what am I left with? Exactly. You're left with this 2 by 2 matrix. So this is how you break down your 3 by 3 into smaller 2 by 2s. So I'm going to do 2 times the determinant of this smaller 2 by 2. And then minus the next number, 5. And then I'm going to multiply that 5 by the determinant of the 2 by 2 matrix, which is formed by crossing out the first row, because 5 is in the first row, and the second column. So you get that 2 by 2 right there. So I get the numbers -1, 3, -2, 4, and then I get plus the last number, -1, and then the 2 by 2 matrix, you cross out first row, third column, you're left with the numbers -1, 1, -2, 3. So just like what I was saying above, how do you calculate the determinant of a 3 by 3? You break it up into these smaller 2 by 2s, and now we can actually calculate those using the formula. So you'll get 2 times 1 times 4 minus 3 times 3. And I'm keeping the color coding so you can see where the numbers come from. And then minus 5 times -1 times 4 minus 3 times -2. And then finally plus -1 -1 times 3 minus 1 times -2. Which will give you some number. But the whole point is that, well, if you simplify this, what do you get? Apparently 19. I already had it worked out. -19. Okay, but the whole point here is that there's a method to this madness of determinants. Okay, so you could, like, in theory, take a determinant of any size, but it becomes really crazy to do it. Like, to do the determinant of a 5 by 5, you'd have to break that into 4 by 4s, and each of those 4 by 4s would be broken up into 3 by 3s, and then those 3 by 3s would get broken up into 2 by 2s. And you just keep on doing this. It's like a lot of calculation. You'll only have to do up to 3 by 3 for this class. In linear algebra, you'll work with more stuff. Okay. So does it make sense how we calculated this? Any questions about the process? Okay. So it's like, okay, so the cross product is defined to be, they're related. Let's say you want to do the cross product of u and v. The cross product is equal to the determinant, where on the top you put I, J, and K, and then you put the entries in rows of U1, U2, U3, V1, V2, V3. So yeah, they end up. So calculating the cross product is related to calculating the determinant. But the cross product formula is not the determinant formula. You use the determinant formula when you calculate the cross product. Does that answer your question? Cool. Okay. So there's some interesting applications to this stuff. You might be wondering, like, why the hell would they come up with this stuff? Like, why? And it's used a lot in computer graphics and in geometry. So, like, you might be wondering, like, how did people come up with this? And then the answer to it is, it sort of arises naturally when you're doing geometry with vectors. So there's a good example of this. So there's something called the triple scalar product. So the triple scalar product is when you have a vector u dotted with v cross w. So you have like the dot product and the cross product. And so there's two ways you can calculate this. You can just calculate it manually by first doing v cross w and then taking that vector and dotting it with u. But interestingly enough, you find out that one way you can calculate this is by doing the determinant of the matrix where you enter these vectors as rows. So you could put u in the first row, v in the second row, and w in the third row. Oops. So if you were to basically make a row matrix by taking those vectors and entering them as rows, and then taking the determinant of that, you would get the same thing if you did u dotted with v cross w, which is sort of surprising. And then you might be wondering, like, okay, cool, so that's like, why do you care about that? Well, let's say you are to draw your three vectors and use them to make a little box. So like u could be the width, v could be the depth, and h could be the height. Oh, sorry, w could be the height. So you could draw a box. So let me show you what I mean by like a box. So I'm gonna put another copy of v right here, and I'm gonna put another copy of u right there. Okay, so can you sort of see? Let me zoom in a little. Does everyone see how u and v like form like my xy plane? And then I could put a copy of w on each of the corners. Oops. Okay, I'm having a hard time drawing. 1 second. You could put a copy of w on each of the corners. And then if I put u up here, hopefully you can see it. Okay, so does it make sense how if you take the three vectors you get a box, or no? We good on like the drawing of the box. I need some reacts. I'm the sad doge. She doesn't know if people are getting it or not. Kind of cool. Okay, crazy thing. If you draw a box like this using U, V, and W, so now that I've got a box, what's like geometrically one of the things you might wonder about this box? Well, boxes don't have area. What do boxes have? Yeah, there you go. You were really close. yeah, I was like, you got it, sort of. So you might want to know what the volume is. Crazy thing. The volume of this box, which we call a parallelepiped. Parallelepiped. A parallelepiped is what you get when you take three vectors and you draw like parallel copies of them to make this boxy thing. The volume of this box is equal to the absolute value of the scalar, triple scalar product. So how did they come up with the triple scalar product? Well, they noticed that if you took the determinant of the three vectors that make your parallelepiped, you basically got the volume. Which is actually sort of crazy when you think about it. So, the determinant of a matrix made from 3 row vectors is the same as the volume of the parallelepiped formed by those 3 vectors. So like this is like one of those first uses of vectors that people probably discovered. At some point they discovered this. They were like, oh shit, like if you want to make some sort of 3D shape, you can form it with 3 vectors. If you want to know the volume of that 3D shape, boom, you just take the determinant. And let's just do like a quick example with something really easy so that we know it's going to work. So this is going to be my U, and let's just say that U is 5, 0, 0. And my V is going to look like this. We're going to make it 0, 5, 0. And then my W will be, I don't know, 0, 0, 2. Alright, so you get this like box. Just quickly like draw it in here. Something like this. Boom. I think you could probably see the box now. Boom. Okay, so we know that the area, the volume of this thing is equal to the base times the width times the height, which is going to be 50, right? Like just looking at this, the way I've set it up is that it has length, those dimensions, 5 by 5 by 2. And it's pretty surprising that you go and you make your vector. We'll enter in the order U, V, W. So we'll have 0, 5, 0. Oops, sorry. U is 5, 0, 0. V is 0, 5, 0. And then the other one is 0, 0, 2. Then you do your calculations. You have the 5 times the absolute value of 0, 0, 0, 2 minus, you have a 0, 0, 0. Oh, wait. I screwed up. You start with this 5, so you get, the numbers we're going to get are 5, 0, 0, 2. There we go. And then minus, you start with this 0. The matrix you get is 0, 0, 0, 2. And then plus that 0, 0, 0, 5, 0. And then because you have zeros out in front of these, it doesn't matter what those are, they just disappear. And then so you're like, okay, let's calculate the determinant of this 2 by 2 right here. You do 5 times 2 minus 0 times 0. That's 0, so it goes away. And then what do you get? You literally just get 5 times 5 times 2, which is the 50 that we were expecting, which is sort of cool. It works out. And you could obviously do this with like more complicated vectors. Like I just wanted to choose a really easy example so that it wouldn't take too long. So if you have like, shapes that have like more, like that just aren't like, orthogonal to each other. Maybe something where it's like, sort of like the base is more stretched out, and then like the way that the height would work, it sort of slants or something. Either way, it calculates in the same way. It's just a parallelepiped. Okay. So I'm going to pause for a moment. Are there any questions? Has everyone seen the video of the guy who lectured for 2 hours on mute? Have we heard about this? We're going to take just a moment. I'm going to show you. It was hilarious. Let me Google it. He was from Singapore. Oh my god. Someone says their professor did the same thing. And the funny thing is he was a math professor, this dude. Here, let me share the page. I gotta share the screen. Does everyone see the screen? Professor realizes at end of 2-hour Zoom lecture that he was on mute. So I'm gonna turn on. Okay, watch this. It's freaking hilarious. Look at his face! Look at his face! He's literally having a breakdown. He's just oh shit. Oh my god! Oh, sometimes. So anyways, there you go. They did. They even tried calling his phone. But he apparently had his phone on mute. Or silent, or whatever it is, do not disturb. There we go. Yeah, I know. They were straight up calling him dude, we can't hear you. We can't hear you. Yeah, I know. He looks so sad. He literally starts going he's like, oh shit, I'm gonna get fired or something. It's so bad. So anyways, I always think of that now. Whenever I'm lecturing, I'm like, oh god. What if everyone just walked away and I'm just speaking into the void or they can't hear me? Okay. Let's talk about another usage of what's it called? So you can use determinants to calculate the areas of these shapes. Parallelepipeds. There's another really cool usage. Torque. Torque is calculated with a cross product. So, let me draw a little picture here. Let's say that you have a bolt. Does everyone see my cool screw bolt or whatever? Those are the threads. It's actually not a bad drawing. Try imitating me. Oh, that's hilarious. So here's my little bolt. And you can tighten the bolt with a wrench. Or not a wrench. What's the word here? In Britain, they'd call it a spanner. What is this? Is this a wrench? What the hell is this thing called? Is it a wrench? I don't know. I can't think. Yeah, okay, cool. It is a wrench. Okay, so how would you tighten this thing? What would you have to do? Turn it righty-tighty. Yes. So you would turn the thing to the right. Wait. Other way. Yeah, like this. Which really, the way you think about it is that you should do it clockwise. Right? So clockwise would tighten it. Now, here's the cool thing about how this works. So, we're going to draw this as some vectors. So, when you turn it, you're applying a vector of force here. Does that make sense? You apply this pressure at the end of the wrench. We'll call that our force vector. And there's another vector which you could think of that starts right here and goes out to here. That's our radius vector. Because if you know anything about physics, what happens to the... So if you have a very small wrench and you try to turn a bolt, how is the effectiveness of that compared to the same amount of pushing but with a really long wrench? So if you have a really long wrench versus a very short wrench and you push them equally, what happens? What ends up being, for people who have had to deal with wrenches, which is more effective, a very long wrench or a very short wrench? Yeah, exactly. So a longer one is easier. So, interesting thing, So torque has to do with this. When you spin or turn the wrench, the torque is what causes the screw or bolt to tighten, and that causes it to turn. So, and it's the product of how long the wrench is, that's the radius, and how much force you apply with the wrench. That's like that. Now, as the screw turns, what happens to the bolt? Or sorry, as the bolt turns, what happens to it? It goes down, right? And that is actually orthogonal to the force vector where you push and the radius vector, the length of the wrench. So the torque, it's this tau. That's the amount of force that pushes the thing down. And crazy thing, the torque that you apply is equal to the cross product of the radial vector and the force vector. The bigger your radius gets, the more torque. In other words, the more force applied to move the bolt down. So there's two ways that you can more effectively move a bolt. You can get a longer wrench and push with the same force, or you could just push it harder. And you can actually calculate like, oh, well, if I need so much pressure to insert the bolt, you can figure out like how long of a wrench you need and how hard you need to push it. So this actually ends up being one of the cool applications of this. That you can use this to figure out like these torques from, you know, because there's it's angular, right? You turn the bolt, right? And that happens from the swinging, and then you get a downward movement, right? So you have your wrench like this, you apply a force, and then it ends up going down perpendicular, right, as you turn it. And we know that the cross product is how you get, if you have two vectors and you want something orthogonal to them, you use that. Yeah, the torque symbol is a tau in Greek. It's like, you go like this and then like that. Do you know about that one? Yeah, it's a tau. I think it's a tau. Yeah, it's tau. So torque is the tendency to produce rotation.